So here's another example problem. An enzyme catalyzed reaction was carried out with the substrate concentration initially 100 times greater than the Km for that substrate. Okay, so if you remember, your Km is the amount of your substrate or the concentration of your substrate that gets your enzyme to half of its maximum velocity. So now what we've done is we said, all right, well, you need this much. We're going to do 100 times that. After 5 minutes, so here's time consideration. So after 5 minutes, 32 micromoles of the product were formed. Okay, so we're generating a product, and this is the time frame. In a separate experiment, 1/4 as much enzyme and 3 times as much substrate were combined. Okay, so now what did we do? We took the amount of enzyme and cut it by 75%, and then 3 times the substrate to monitor that reaction. In 5 minutes, how much product would be formed in the second reaction? Okay, so reaction 1 is, well, your substrate concentration is 100 times your Km. In R sub 2, or your second reaction, we have your substrate concentration is 300 times your Km, but your enzyme concentration is dropped by 75%. If 32 micromoles of the product times 4, or times 1/4, that would be 8 micromoles of the product in 5 minutes. Okay, so if we have 1/4 as much enzyme, we're going to make 1/4 the amount of our product. Now, in the second reaction, how long will it take for 32 micromoles of that product to be produced? Well, we have to spend 4 times as much time. So reaction number 1, 32 micromoles, 5 minutes. Reaction 2 would be 32 micromoles in 20 minutes. Okay, so just an example, and this is, I don't think that this is, there's no like secret sauce to this. This is effectively saying that what matters is the amount of your enzyme, not so much the amount of your substrate. Because if you remember, in reaction number 2, we had 300 times the Km. Reaction number 1, we had 100 times the Km. No matter how you throw the or inflate the amount of substrate, it doesn't change the reaction rate. Okay, so Lineweaver Burk double reciprocal plots. It's difficult to determine the maximum velocity experimentally, because if you look at these other reactions, what you're doing is you're just trying over and over again to increase the substrate concentration, and you might do 30 different reactions here, here. So we have to find another way. So another way of doing that same sort of thing, and to get a good prediction of your Km and your Vmax, is to make what's known as a Lineweaver Burk plot, also known as a double reciprocal plot. And essentially what you're doing with this is you're taking that nonlinear data, that hyperbolic data, and you are making a linear plot. So the equation for a hyperbola can be transformed into the equation for a straight line by taking the reciprocal of each side. Now I like this equation, and I like this graph a little bit more than, say, your hill plot, because you can linearize this nonlinear data, and you don't have to use a bunch of log expressions. So that's just a personal preference. The formula for a straight line is y equals mx plus b, and you know what? Your y is 1 over your velocity, which then your m is your slope of your line, is Km over Vmax. Your x-intercept is 1 over substrate concentration, and your x value is 1 over substrate concentration, and your y-intercept is 1 over maximum velocity. So a plot of 1 over velocity, so inverse velocity versus inverse substrate concentration will give you a nice straight line with a slope that is Km over Vmax and a y-intercept that's 1 over Vmax. Yeah, Km over Vmax. This is known as a double reciprocal plot, and here's ultimately what it looks like. The way that I always think about this is I think, okay, what are my axes? I'm concerned with an x and a y axis. My y-axis is 1 over my velocity. My x-axis is 1 over my substrate. So when you go through and analyze an enzyme, what you're going to do is you're going to do a series of trials, 1, 2, 3, 4, 5 trials, where you will use varying amounts or varying substrate concentrations. And for those substrate concentrations, you will ultimately collect velocities. So substrate concentration 0.2, 0.4, 0.6, 0.8, and 1.2. We'll just say those, okay? Now, for each one of those trials, you'll get a velocity 13, 26, 29, 30, 29. In order to make this Lineweaver-Burk double reciprocal plot, all that you're going to do is take this data, the substrate data, and this velocity data, and you're going to say 1 over 0.2, 1 over 0.4, 1 over 0.6, 1 over 0.8, and 1 over 1.2. Then for velocity, you'll look at and you'll make a, sorry, this is 1 over substrate concentration. We'll make 1 over velocity, 1 over 13, 1 over 26, 1 over 29, 1 over 30, 1 over 29. And again, what's important to know about those numbers is those numbers I just kind of made up. It doesn't really matter what those numbers are. The key is whatever your substrate concentration is, you get the reciprocal of it. Whatever your velocity is, you get the reciprocal of it. These 2 points are your x and your y coordinates respectively. And so you'd plot that. You'd say 1 over 0.2 is approximately this, or sorry, it's right here. 1 over 13 is approximately right here. So boom, there's my data point. 1 over 0.4 is right here. 1 over 26 is about right here. So you ultimately come up with a plot that looks like that for a Lineweaver-Burk double reciprocal plot. So you'll plot all those data, and what you'll ultimately come up with is a nice graph that shows your y-intercept value. So your y-intercept, your x value here, your x, y coordinates are 0, and in this case, 0.1. Your x-intercept is where this would happen to be -5, 0. The x value is -5 and the y-intercept is 0. From those data, you can come up with what is your Km and what is your Vmax respectively. If your y-intercept is 0.1, you set that equal to 1 over Vmax. Well, multiply each side by Vmax, and then you end up with Vmax equals 10. If your Km is, or sorry, if your x-intercept is -5, you set that equal to -1 over Km. And you get Km is equal to 0.2. So that's, I think, a cleaner and easier way to come up with data and to come up with these important kinetic parameters, your Km and your Vmax respectively. It tells you how quickly an enzyme can possibly go and how much substrate is needed to get there and the affinity that your enzyme has for that substrate. Ultimately, what's the significance of Km? Well, Km is really a ratio, in addition to what I've already talked about. It's a ratio of rate constants. It looks at your forward reaction and your reverse reactions and relates them to one another. Km is equal to, well, these two, K sub -1 and K sub 2. these two are the breakup of ES. Whereas this rate constant, this K sub 1, is the formation of ES. So basically, Km is comparing, is ES being broken down or is it being made up? Now, when K sub 2, the okay, there we go. When K sub 2 is considerably less than K sub minus 1, this and this, then Km reduces to K sub minus 1 over K sub 1, which is the same as your dissociation of that ES complex. Under these conditions, Km can be equated to the dissociation constant. Therefore, all small Km's mean very tight binding, which means a high Km means a very weak binding. So that tight binding means strong affinity. So when the Km is very high, you have weak binding, you have low affinity. When Km is very low, you have very high or tight binding and very high affinity. Now, ways that you can use Km. You can compare Km for different substrates for one enzyme. So you can compare the Km for different substrates for one enzyme. And an example of that would be the enzyme hexokinase. Hexokinase is an enzyme that takes two things, ATP and glucose, and it is a transferase, it is a sugar kinase. So what it makes are ADP and glucose 6-phosphate. So this is an enzyme that will catalyze this reaction. It has these two unique substrates, and it binds to both of these substrates with different affinities. So it binds to ATP with a Km of approximately 0.4 millimolar and glucose with a Km of approximately 0.05. So between those two, which one is it going to bind more tightly? The lower the Km, the higher the affinity. And the tighter that it binds. So it's going to bind to glucose more tightly than it does to ATP. Fructose is another 6-carbon sugar. Fructose is kind of your glucose derivative or your ketose glucose, and it has a Km of 1.5 millimolar. So what you could do is you could ask yourself, given, or if you gave hexokinase both glucose and fructose, which one is it going to bind to more or preferentially? Does it have a greater affinity for one over the other? Yes, it does. It's more likely to bind glucose than fructose. So if both sugars were at a concentration of 5 millimolar, with which sugar would the enzyme be operating at Vmax? Okay, so if both of them are at 5 millimolar, let's go ahead and plot this out. I'm going to do the glucose graph. That looks a little bit like this. And here's 1.5. And here's your half Vmax. 5 millimolars over here. And then your other one looks like this. And we've got 0.05 and 1.5. Here's 5 millimolar. Really, it's going to be operating very close to Vmax with both of them, because the concentration of the sugar, or the concentration of each sugar, is greater than the Km that this enzyme has for both of these sugars. Now, is there one that is going to be going a little bit faster? Absolutely. It's going to be going a little bit faster in the presence of glucose, or with the glucose, because the concentration of glucose is 5 millimolar when its Km is 0.05 millimolar. So that's a 100-fold difference. In addition to that, Km can be used to compare a common substrate amongst two enzymes. For instance, hexokinase is an enzyme that's in basically every cell. Glucokinase is something that's much more abundant in the liver. Both of these enzymes will bind glucose. Glucokinase has a Km of 20 millimolar, whereas hexokinase has a Km for glucose of 0.05 millimolar. Which one is it going to bind, or which enzyme is going to bind glucose more tightly? Hexokinase. Glucokinase will bind it, but with a much lower affinity because of the fact that the Km is 20 millimolar. Which enzyme is operating at Vmax when the glucose concentration is 4 millimolar? Let's think about this. Glucokinase needs a concentration of 20 millimolar in order to be going as half as fast as it needs to go, or it can go. If you give it 4 millimolar, that's 1/5. That's 20% of what it needs. So super low velocity, not even close to your Vmax. So make sure that you can do those sorts of comparisons. Meanwhile, hexokinase, again, 0.05 millimolar. If you give it 4 millimolar glucose, it's just happy as a clam. It has well more than it needs. Now, disadvantage of Vmax. The Vmax is the maximal velocity. And that maximal velocity, but that's proportional to the enzyme concentration at a given time. This is a problem if you don't know the concentration of that enzyme at a given time. And therefore, it's hard to qualitatively look at Vmax. In order to compare your Vmax of various proteins, we must know the enzyme concentration at a given time and the number of enzyme active sites. A protein must be pure to calculate your enzyme concentration at a given time. Instead of looking at maximum velocity, we'll look at maximum, or your corrected maximum velocity, for the total amount of enzyme active sites in solution. So we use something known as a turnover number, or your kcat, which is your maximum velocity over your enzyme concentration at a given time. Now, this turnover number, the significance of this is a measure of catalytic activity. When your enzyme is saturated with the substrate, the observed turnover, or the observed rate constant, is the turnover number. The turnover number is the number of substrate molecules converted to product per enzyme active site per unit of time. And what's important to think about here is there are enzymes similar to a protein like hemoglobin. Hemoglobin has 4 O2 binding sites. There are enzymes that have 4 active sites or 6 active sites, so they can bind 6 copies of the substrate and convert it to a product. And we use kcat as a kind of a measure or a way of reconciling that. So kcat is your maximum velocity divided by your enzyme concentration at a given time. Now, to consider this, the maximum velocity for this conversion of a substrate to a product under saturating conditions for these two different enzymes, ATMase and UTase, is 10 micromole of substrate to product per second. So if 2 micromoles of the enzyme ATMase catalyzes the reaction, what is the kcat? In order to calculate this, your Vmax divided by enzyme concentration, 10 micromoles divided by 2 micromoles, is a kcat measure of 5 per second. This means that ATMase catalyzes the conversion of 5 substrates to product every single second. And now TUase is another enzyme that has 4 active sites per mole of enzyme. So if 2 micromoles of the enzyme TUase catalyzes this reaction, what is the kcat? Well, we have to consider the active sites. We have a total of 4 active sites. That means we have 8 micromoles of active sites. So what we do is we look at what is our maximum velocity, which is 10 divided by 8. And this enzyme ultimately has a kcat of 1.25 per second. this means that this enzyme converts 1.25 substrates to product per second. So the number of active sites basically implicates this TUase as kind of, in some respects, being slower, because it has the same maximum velocity, but each one of those active sites is moving that substrate to a product at a slower rate. And so between these two, the enzyme that has the higher Kcat is the one that's more catalytically active. So if we jump back and look at this table right here, the higher the Kcat, you could kind of look at it as which is better, the higher Kcat or the lower the Kcat? The higher the Kcat, because that means it's producing this many substrates per second, or sorry, substrate converted to product per second. Now, an advantage of Vmax, it can be used to provide a quantitative measure of the enzyme's concentration. So specific activity is a measure of activity per amount of protein. We previously talked about specific activity when we were talking about purifying a protein. And specific activity was used as our measure of ultimately the purity of a protein. Specific activity is the number of substrate molecules converted to product per amount of total protein present when E is saturated with your substrate. Specific activity increases until the total protein present is E, at which time it will reach a maximum. Increasing the amount of pure enzyme will not increase specific activity, since under saturating conditions, the velocity is proportional to the amount of enzyme present. So therefore, under a given set of conditions, a particular enzyme should always have the same specific activity so long as it's pure. Now, I'm not going to ask you to do any sorts of calculations for this, because this is kind of, in some respects, this is tweaking, adjusting the units, but effectively looking at what we previously saw. So I'm not going to ask you to do this and know this for the exam. So I'm just going to leave this as is. A solution containing 25 milligrams of total protein catalyzes a conversion of 14,250 micromoles of substrate to product per second. And therefore, we divide 14,250 divided by 25 gives us 579 specific activity. And if the pure protein catalyzes a conversion of 1456 micromole per mil substrate to product, what's the specific activity of the solution? It's going to be 728 micromole per second per milligram. What's the percent purity? Well, we're comparing specific activity of the solution to that pure protein, and we get 79%. So this is another way of looking at a known pure protein versus a solution and how pure that protein is. The relationship between specific activity and turnover number is important because specific activity is the activity per amount of protein. Kcat is equal to Vmax divided by enzyme at a given time. Kcat is equal to specific activity times molecular weight per active site. I'm also not going to ask you to solve any questions or address any calculations like this. And in fact, I'm going to jump ahead to basically, let's see. Let's see, just a second. Yeah, this next slide, and then I've got a couple more. Catalytic efficiency is something that we are concerned with and we want to know about because we want ultimately very efficient enzymes. And a way that we can determine catalytic efficiency is by comparing the catalytic activity of an enzyme, or your Kcat, over Km. An estimate of how perfect or efficient the enzyme is, excuse me, Kcat over Km is an apparent second order rate constant. It measures how the enzyme performs when substrate concentration is low. The upper limit for Kcat over Km is the diffusion limit, the rate at which enzyme and substrate diffuse together. Now, ultimately, if we look at Km being a higher number, or a way that we can look at this is we want an enzyme to have a low Km and a high Kcat. that will give us our largest ratio of kcat over km, because we want the enzyme to bind very tightly, so grab onto that extremely small concentration of your substrate, so a very low km, and then turn that substrate into product very rapidly. So when we have a 9 times 10 to the negative fifth and 1.4 times 10 to the fourth, we get a very high kcat over km ratio. So I want you to be able to do that sort of calculation. And I want you to understand that catalytic efficiency is a ratio of kcat over km. Now, I'm going to skip the next little bit of this because ultimately what I want to get to is an example. And an example of kind of looking at plotting data. So I've given you the Michaelis-Menton equation, and I will give you that Michaelis-Menton equation on the final exam. As a graduate student, there was a professor who I worked with who he did this Oreo cookie lyase experiment. And what this experiment consisted of was people would be handed Oreos and told, hey, you are a person who has an Oreo and you can convert this into a product. Your substrate is the Oreo, your product is that Oreo that's been twisted apart. Cookie lyase is the name of the enzyme. It twists an Oreo apart. This is not a real enzyme. This is simply an example in a model. And in order to determine the kinetic parameters of the cookie lyase, several experiments are performed. So what we would do is we would set students out at different desks and distribute Oreos in a ratio of number of Oreos per desk. And we started out with 5 desks out, or 5 desks, and you would give 1 Oreo per 5 desks. And then the ratio would increase 1 Oreo per every 4 desks, 1 Oreo per every 3, 2, and then ultimately when you had these 5 desks, so those are my 5 desks where people were seated, you would start out with 1 Oreo here, and then you would time for 10 seconds. And say, okay, well, after 10 seconds, how many Oreos are lysed? And the answer was 3. Then you'd say, all right, well, ultimately in trial number 5, if we put 1 Oreo at each desk, and set a timer for 10 seconds, and started the timer, and then whenever someone would show you a product, you replenish and you give them another Oreo so they could twist it. And what you got was, well, if you put 1 Oreo at each of 5 desks, and you had 1 person seated at each of those 5 desks, and you gave them 10 seconds to twist Oreos apart, you get about 10. When you'd increase the number of Oreos, 2 Oreos per desk, you're providing more and more substrate. You get more and more product. At some point, though, we would put 5 Oreos, 3, 4, 5, 3, 4, 5, 3, 3, 3, 4, 4, 4, 5, 5, 5. 5 Oreos per desk, give them 10 seconds, and you'd get 16 Oreos on the other side. You'd give them that time, they would break those Oreos open, and boom, we're done. Okay. Now, if you look at these numbers, 1 Oreo per desk, 5 Oreos per desk, the number of Oreos that were converted into the product, well, it didn't really escalate a huge amount. We went from 10 to 16. So at some point, the number of Oreos or the amount of substrate at each desk presented the problem. You could take that same data and come up with a graph that looks like this. Y-axis is our velocity, our number of Oreos lysed in 10 seconds, versus x-axis, which is the number of cookies per desk. As we increase the number of cookies at each desk, the velocity or the rate didn't really escalate. Sure, it went up, but not nearly as much as initially. And so we would see this plateau effect. So then what we would do is we'd take that same data, this 1 per 5, and do the reciprocal of that, 1 over 5, and we get 5. Take all of these data, take the reciprocal of all of those data, plot them here. Then this data set, this velocity, number of Oreos lysed in 10 seconds. We would take that and take the reciprocal of that and get this plot. We could do a double reciprocal or a Lineweaver Burk plot, and it would look like this. And you know what? Whenever we did that, we could have a line y equals mx plus b and figure out, okay, well, here is our x-intercept. That's negative 1.4. Our y-intercept is 0.075. Well, those values equal to negative 1 over km, equal to 1 over Vmax. You do the algebra and solve for your km, solve for your Vmax. This is just a model representation of basically how you process or how you run an experiment. For enzyme kinetics, you increase the amount of substrate, you monitor the product formation in order to determine your Km and your Vmax, these two very important kinetic parameters or enzyme kinetic parameters. All right, well, that wraps up this first day of enzyme kinetics, and I'll see you in the next video. Have a good one.